Welcome to Topic 1901, Urban Stormwater Management. This presentation introduces stormwater management from an ecological planning perspective and explains why it has become a major issue in contemporary urban design and climate adaptation. Rather than treating stormwater as a purely technical drainage matter, this topic approaches it as a planning challenge that affects spatial organization, ecological performance, infrastructure resilience, and urban quality of life. Throughout the presentation, the focus is on how cities can respond to increasing runoff, flood risk, and water quality pressures by moving beyond conventional gray infrastructure alone. The lecture also highlights how nature-based solutions, digital tools, and integrated planning strategies can support more resilient urban environments. In this sense, the topic is not only about water management, but also about how stormwater can be understood as part of a broader ecological and spatial system within the city. This presentation is organized as a planning sequence. It begins by explaining why stormwater has become a planning issue in today's urban environments. It then moves into the main ecological principles and policy frameworks that guide contemporary stormwater thinking. After that, the lecture reviews the main nature-based measures and shows how they operate across different planning scales, from the parcel to the catchment. The next part introduces digital tools that support risk analysis, modeling, and design coordination. The final sections focus on case studies, transferable lessons, and a practical checklist for implementation. This sequence is important because it mirrors the way planners and designers actually work. First, they need to understand the problem. Second, they need an ecological and policy framework. Third, they need to choose measures and test them. Finally, they need to translate those ideas into feasible and maintainable planning practice. The learning objectives of this topic are structured around knowledge, analytical skill, design ability, and professional attitude. First, the lecture aims to explain stormwater management as an ecological and climate adaptation planning challenge. Second, it introduces key planning frameworks such as nature-based solutions, SUDS, LID, WSUD, and integrated urban water management. Third, it emphasizes the role of GIS, modeling, and digital design workflows in supporting risk analysis and scenario testing at the catchment scale. Fourth, it focuses on the selection of multifunctional green infrastructure measures that can retain, slow, clean, and safely route water. Finally, it underlines the importance of interdisciplinary, inclusive, and maintenance-aware implementation strategies. Together, these objectives show that the topic is not limited to technical knowledge. It also requires the ability to interpret planning language, evaluate alternatives, and think about long-term performance, governance, and social responsibility in stormwater planning. Stormwater has become a planning issue because urbanization, intense rainfall, and impervious surfaces are changing the way water behaves in cities. As natural ground is replaced by roads, roofs, and other hard surfaces, infiltration decreases and runoff increases. This means that more water moves across urban surfaces more quickly, creating larger runoff volumes and faster peak flows. At the same time, many cities continue to rely on combined sewers and aging drainage systems that are often undersized or poorly maintained. As a result, flooding, sewer overload, and water quality decline become more likely. The issue is also ecological and social. Pollution, urban heat, and habitat loss can intensify the effects of stormwater problems. In addition, dense neighborhoods, low-income communities, and infrastructure-stressed areas often face greater exposure to these risks. For this reason, stormwater is no longer only about drainage. It is also about hydrology, infrastructure, ecology, spatial planning, and equity. This slide explains the major paradigm shift from conventional drainage logic to ecological planning logic. In the conventional approach, the goal is to collect water quickly, convey it away, treat it downstream, and hide the infrastructure from view. This produces systems that are often centralized, single-function, and highly dependent on buried pipes and engineered channels. In contrast, ecological planning focuses on retaining water near its source, delaying flows, promoting infiltration, and reusing water where possible. It also treats water as a visible part of the landscape rather than something that must always be hidden underground. This shift is important because it expands the role of stormwater systems. Instead of only moving water away, ecological systems can generate co-benefits such as biodiversity support, public space quality, cooling, and distributed resilience. The key message is not that pipes disappear, but that cities reduce their dependence on single centralized systems by combining technical infrastructure with landscape-based and multifunctional solutions. Different regions and planning traditions use different terms to describe contemporary stormwater management. These include LID, SUDS, WSUD, Sponge City, and One Water. Although the terminology varies, the shared message is broadly consistent. Water should be managed as part of urban form, not only through buried infrastructure. Nature-based measures should address flooding, water quality, biodiversity, and public space together. Planning should also connect multiple scales, including the parcel, the street, the district, and the catchment. For Topic 1901, the important point is to understand these frameworks not as labels only, but as ways of translating climate adaptation goals into spatial planning and design decisions. Ecological planning makes blue-green systems part of everyday urban structure. At the same time, the slide reminds us that no single framework is universally best. The most appropriate approach depends on local hydrology, governance capacity, institutional structure, and long-term maintenance conditions. This slide introduces the Oslo three-step strategy as a clear and memorable planning heuristic. The first step is to catch, clean, and infiltrate small rainfall events. The second step is to delay and retain larger events before release. The third step is to divert extreme events through safe surface floodways. This sequence is valuable because it shows that different rainfall conditions require different responses. Routine storms should be managed locally through everyday infiltration and small-scale retention. Larger events require temporary storage and controlled release. Extreme events, however, must also be acknowledged openly, and cities need visible, safe overflow pathways to manage them. The planning value of this approach lies in combining ordinary and extraordinary water management within one coherent system. Rather than relying on a single device or one hidden network, the strategy emphasizes sequencing, redundancy, and surface-based safety. In this way, hydrologic logic becomes directly connected to urban design and emergency resilience. Nature-based stormwater management depends on combining several different measures rather than expecting one solution to solve the entire problem. This slide presents a basic palette of measures. Green roofs can detain water, reduce heat, and support biodiversity. Rain gardens and bioretention systems can infiltrate and filter runoff. Vegetated swales can slow flows, convey water, and provide pre-treatment. Permeable pavements reduce directly connected imperviousness and help water move into the ground. Retention and detention spaces can store water and reduce peak flows. Open streams and floodways make overflow visible and route excess water more safely. The important message is that these measures have different functions, including capture, filtration, infiltration, storage, evapotranspiration, and safe conveyance. Their effectiveness increases when they are combined thoughtfully. In ecological planning, the goal is not only hydraulic performance, but also the creation of multifunctional urban systems that support environmental quality and visible resilience within the built landscape. Stormwater planning must work across scales. At the parcel level, interventions may include roofs, courtyards, and storage tanks. At the street level, planners can introduce swales, curb cuts, and permeable paving. At the district or block level, larger interventions such as parks, basins, and open channels become important. At the catchment scale, planning decisions involve zoning, flood routes, and investment priorities. The core lesson of this slide is that stormwater planning often fails when the scale of diagnosis does not match the scale of intervention. Small parcel-level measures are useful, but they cannot fully solve a problem that is shaped by catchment-wide water behavior. Water accumulates according to larger topographic and infrastructural conditions, and overload risk often appears beyond the individual site. For that reason, planners must connect micro-scale design measures with meso- and macro-scale analysis. Ecological stormwater management becomes more effective when parcel, street, district, and catchment are treated as parts of one system. Digital tools support better evidence for stormwater planning and design decisions. GIS mapping helps identify catchments, inlets, land cover patterns, and risk hotspots. Runoff and flood modeling help estimate volumes, flow paths, overflow behavior, and bottlenecks. BIM and parametric design workflows support design coordination, grading, and detailed spatial integration. Scenario testing makes it possible to compare the size, location, phasing, and trade-offs of different facilities and strategies. The key point is that digital tools are not used for complexity alone. Their value lies in improving catchment understanding, testing alternatives, and supporting decision-making with clearer evidence. In this topic, digital literacy is important because ecological stormwater planning depends on understanding both spatial patterns and system performance. These tools help planners move from general concepts toward more informed and defensible interventions. They also make it easier to compare different approaches before implementation and to align hydrologic logic with urban design, investment priorities, and long-term planning decisions. Good performance in ecological stormwater planning cannot be judged by hydraulic capacity alone. This slide presents a broader understanding of performance. In terms of flood risk, successful systems lower peak flows, slow runoff, and create safer overland routes. In terms of water quality, they help filter sediments, nutrients, and pollutants. For urban heat, shade and evapotranspiration can cool surfaces and improve thermal comfort. In relation to biodiversity, native planting can support habitat and ecological connectivity. In terms of amenity, visible water landscapes can improve the quality of the public realm. Finally, equity and maintenance must also be considered, because benefits should remain legible, accessible, and serviceable over time. This multi-dimensional understanding of performance is essential in ecological planning. Stormwater interventions are valuable not only when they move water effectively, but when they also contribute to healthier, more inclusive, and more resilient urban environments. Co-benefits are therefore part of the design objective, not merely secondary outcomes. One of the strongest messages in the literature is that implementation barriers are rarely only technical. This slide groups barriers into three categories: technical and spatial, governance and finance, and operations and culture. Technical and spatial barriers include dense retrofit conditions, soil limitations, legacy sewers, and uncertain climate loads. Governance and finance barriers include siloed agencies, path dependence, weak funding for distributed systems, and uneven standards. Operations and cultural barriers include maintenance neglect, low public awareness, poor monitoring, and unfair distribution of benefits. This means that good stormwater planning cannot stop at design. It also needs to address institutional coordination, financial capacity, long-term stewardship, and implementation culture. Even strong ecological ideas can fail if they are introduced into fragmented systems without clear responsibilities. For this reason, ecological planning must include governance logic alongside hydrologic and spatial logic. A resilient stormwater system depends not only on what is built, but also on who manages it, funds it, and maintains it over time. This slide summarizes the common direction of the review literature. First, research is shifting from general concepts toward more specific technical roadmaps and more integrated, multifunctional approaches. Second, integrated stormwater management works best when planning, ecology, infrastructure, and social inclusion are addressed together rather than separately. Third, green infrastructure, modeling tools, and vulnerability analysis are now central to contemporary flood control practice. These points show that the field has moved beyond asking whether ecological stormwater management matters. The current focus is increasingly on how to locate, size, coordinate, govern, and maintain measures in real urban conditions. This is important because it reinforces the idea that successful stormwater planning must be both technically informed and spatially strategic. The literature supports an integrated direction in which urban resilience is achieved not through isolated devices, but through combinations of ecological thinking, digital analysis, planning coordination, and attention to vulnerable populations and uneven urban conditions. This slide turns theory into a practical workflow that planning teams can follow. The first step is diagnosis, including catchments and hotspots. The second step is to set targets related to retention, risk reduction, and co-benefits. The third step is to select measures according to scale and site fit. The fourth step is to model scenarios in order to compare size, overflow behavior, and trade-offs. The fifth step is to phase delivery, which involves funding, governance, and operations and maintenance. The final step is to monitor and adapt performance over time. This workflow is important because it shows that ecological stormwater planning is not a one-time design act. It is a process that begins with analysis and continues through implementation, stewardship, and revision. A particularly important point is that maintenance and governance enter the workflow before the end of the project, not after construction. Monitoring then closes the loop and helps the system adapt as urban and climatic conditions change. The Oslo case is presented as a strong example of combining blue-green systems with safe surface routing. Its central logic is the three-step strategy introduced earlier: manage small events locally, delay larger events, and route extreme events safely across the surface. In practice, this involves the use of blue-green roofs, rainbeds, and open streams, while also designing roads and streets as emergency floodways when needed. Another key idea is that cross-sections should be tailored to local climate and topography. This means that the system is not based on one standard solution, but on spatial adaptation to context. The case is also important because it treats stormwater as a civic landscape resource rather than only as a technical burden. Everyday water management and extreme event safety are coordinated through visible urban design elements. The planning lesson from Oslo is that resilience becomes stronger when water is integrated into public space, landscape structure, and street design in a deliberate and legible way. This case focuses on a residential settlement in Edirne and shows how vegetation-led strategies can manage runoff at the scale of streets and housing environments. The study analyzes existing topography, flow directions, and vegetation texture, and then uses plant-based green infrastructure to keep runoff within streets and the wider site. The aim is to improve infiltration, reduce surface flow, and support urban environmental quality. This case is useful because it operates at a scale that many planners frequently encounter in practice. Instead of relying only on large downstream infrastructure, it begins with a close reading of local landscape conditions and uses vegetation as a functional water management strategy. The planning value here lies in demonstrating that stormwater measures can be embedded into everyday residential environments. Planting, surface treatment, and site structure become part of a system that responds to runoff behavior while also improving the environmental quality of the neighborhood as a whole. This slide highlights the value of transferable techniques such as bioretention basins, permeable pavement, grassed swales, and infiltration basins for reducing runoff volume in urban areas. The main planning message is simple but significant. Rather than searching for one universal solution, planners should combine several small, context-fit measures. This is especially relevant in retrofit settings, where space is limited and site conditions vary from one location to another. The importance of these techniques lies not only in their hydraulic function, but also in their adaptability. They can be combined differently depending on local street conditions, site constraints, and neighborhood characteristics. This makes them useful across a wide range of urban contexts. The slide therefore reinforces a key theme of the lecture. Ecological stormwater planning works best when it is distributed, flexible, and based on multiple measures that complement one another. Local effectiveness is strengthened when techniques are selected and combined according to actual site conditions. Across the case material, successful projects share several common characteristics. First, source control comes first, but overflow is also planned explicitly. Second, the measures are visible, legible, and maintainable. Third, the design works across scales instead of being limited to isolated pilot objects. Fourth, co-benefits are treated as design objectives rather than accidental side effects. Fifth, institutional ownership and maintenance are defined early. Together, these points show that the strongest predictor of success is coherence. Good projects are not only technically correct, they are also understandable, serviceable, and governable over time. They connect hydrologic logic with spatial design and institutional responsibility. This is an important lesson because many projects fail not because the idea is wrong, but because the system is too fragmented, too hidden, or too dependent on unclear responsibilities. Successful ecological stormwater projects create alignment between water processes, visible design, everyday use, and long-term management. This slide translates the lecture into a practical checklist. Planners are encouraged to map catchments before drawing details, size measures for both routine and extreme events, link roofs, streets, and open space into one system, keep maintenance access simple and obvious, and prioritize retrofits where risk and vulnerability overlap. At the same time, several common mistakes should be avoided. Planting should not be treated as decoration only. Overflow pathways should not all be hidden underground. Designers should not depend on one measure type everywhere. Maintenance issues such as sludge, vegetation, and debris should not be ignored. Success should also not be judged only by pipe capacity or construction cost. This checklist is useful because it clearly identifies the operational logic of good practice. It also makes the lecture more actionable for interdisciplinary teams. The central message is that implementation quality depends on scale awareness, visible hydrologic logic, maintainability, and attention to social as well as technical conditions. To conclude, stormwater management is now a core climate adaptation and ecological planning task. The most robust planning logic is to retain water near the source, delay moderate events, and route extreme events safely. Nature-based measures become strongest when they are coordinated across parcel, street, district, and catchment scales rather than used in isolation. GIS, modeling, and digital design tools improve risk analysis and scenario testing, helping planners make more informed and defensible decisions. Finally, the best cases succeed because governance, maintenance, and co-benefits are considered from the beginning. The overall takeaway from topic 1901 is that stormwater should be designed as a visible ecological urban system, not treated as a hidden afterthought. When hydrologic logic, spatial design, digital analysis, and institutional follow-through are aligned, stormwater infrastructure can contribute directly to resilient city-making. In this sense, ecological stormwater planning supports not only flood management, but also broader urban quality, environmental performance, and long-term resilience.